All right. All right. Let's start with day 99, day 98, almost done. 2 more days left. Today I'll be going over semi-supervised learning and weekly supervised learning once again. It's mostly going to be a review because I've gotten most of the work done in the morning. I'm just gonna, I guess, go through it. The power has been very unstable at my house today, so doing this pretty late in the night when I'm assuming that it's stable. Okay, anyways, let me open up my links here. I'll start with this. Snorkel. Okay, so what I read was, I guess it started with weekly supervised learning, what weekly supervised learning is, the different algorithms, and its comparison to semi-supervised learning and transfer learning. Just trying to see what the differences are. And it turns out that, in a way, semi-supervised learning is actually a subset of weekly supervision, and it comes under the category of incomplete supervision. So it's basically the fact that when active learning is occurring, we the data set is actually what determines the incomplete supervision. So what we kind of say is when we have an incomplete supervision, we have a data set that has some parts that are labeled and some parts that are unlabeled. So it's not very messy. There's still a structure to it, and you can use that data set. And by utilizing the labeled data set, we train our algorithm on that, and then use that trained algorithm to predict on the unlabeled data. That's kind of how semi-supervision works. But there's also other kinds where it's inexact supervision and inaccurate supervision, which all include different versions of how the semi-supervised algorithm is set up. In exact supervision, we use a deep learning model, most popularly the CNNs. And in inaccurate supervision, it's kind of similar to unsupervised learning. So the unlabeled instances are kind of raw in nature. It's not really like it's not a clean data set. I guess I have to go through Snorkel and read about that. In fact, I think I'm going to reread this article. I wonder if I can pick up any new nuance. The heck? It's a video. It's a slide. What's going on? Generative models, label propagation, and TSVM. All of things that I should check out. TSVM. Active learning or semi-supervised learning, depending on human intervention. In active learning is used when a domain experts to get labels of unlabeled. Okay, so the domain expert is used to get labels. So the domain expert just labels data, creating active learning. But the cost is high here. On the other hand, semi-supervised learning exploits instances without human intervention, such as generative label propagation and TSVM. Generative methods assume that both labeled and unlabeled instances belong to the same model, so Gaussian mixture distribution. And I think that's what co-training falls under. In this way, labels of unlabeled data can be treated as missing values of model parameters. Label propagation or disagreement-based methods generate multiple models and let learners teach each other to exploit unlabeled data. Okay, hold up, never mind. Label propagation is co-training, I think. Yeah, because in co-training, two predictors are set up against each other, and the better prediction is used as a label for the other predictor. So one two models are running and one model is teaching the other. Whichever model is teaching the other is the one that's performing better for that batch. So another algorithm is transductive support vector machines. Inexact supervision is used in deep learning. CNNs, due to their impressive ability to automatically learn representations across many domains. Representations across many domains. Multi-instance learning, more precisely training set, consists of labeled bags, which collection of unlabeled instances. Hold on, I'm not understanding this. Deep learning, due to their impressive ability to automatically learn representations across many domains, replaced the task of feature engineering. Okay, so it's trying to determine the labels. That's feature engineering. And which labels are important for prediction. Okay, I see. So the deep neural network model here, or CNN, is used to train basically a person who would perform feature engineering. So it's training a feature engineer. And this feature engineering model would basically predict which labels are important and also what combinations. So now for each item can be used multi-instance learning. More precisely, training set consists of labeled bags, which is a collection of unlabeled instances. So it contains a bag of unlabeled instances and multiple bags. A bag is positively labeled if at least one instance in it is positive, and negative labeled if instances in it are negative. So if at least one is positive in the bag, then it's positive. If all are negative, then it's negative. Goal is to predict the labels of unseen bags. So whether it's positive or negative. But what does that even mean? Like, what does positive and negative mean? Okay. This is a little sketchy. I don't understand. Inaccurate supervision uses several learners to identify unlabeled examples and check it with training data to make some corrections. Used for crowdsourcing. Oh, cool. I gotta read this paper from by Snorkel paper. Okay, done with that. Let's read this. Good transition into Snorkel. How Snorkel is semi-supervised learning techniques solved invoice accounting at Tide. Dice Curry. Getting a little lost here. It's the co-training algorithm implemented using TensorFlow. Okay, this is pretty long TensorFlow code, but I think the general gist of it is the fact that it's a co-training implemented with TensorFlow, and it does deep learning on a set of images. The CIFAR10 is an image data set. So these first few methods are for helper methods for loading in that data set right there. And let's see. Yeah, all of this is within the same block till the next div. Wait, where is it? Hold on. Right here. There's a return here. Okay, so this is just written without a definition. It's poorly written code, to be honest. Let's see what it does. Loads in the data set here. What are we doing? Ones and zeros. Okay, I guess we're assigning ones and zeros based on even or odd. So this must be like random. It's not even random. I don't even know what it is. It's just dividing the whole data set into ones and zeros. And I think the ones and zeros are supposed to represent positive and negative values that was discussed shortly in this area right here. All right, so for each bag, a bag is positively labeled and negative labeled if all the instances are negative. But here it doesn't check if it has a positive or negative. It just does it based on odd or even. Oh wait, I think it's literally just assigning every single instance, because while it's not one, and so everything but one is a zero. Now we have the positive and negative counters. What's going on here? In range X train, if positive counter is equal to labeled data set size divided by 10 and negative counter is equal to divided by 10, then break. So every 10th it's breaking. Y train is 1, else. So if at first, at our first I, which is 1, it would be 1. So it would come in here. If positive counter is equal to label that data size divided by 10, continue. I don't know what this line of code does. Positive counter plus equals 1. So it's counting positive labels, and this would count as a positive label. L.append, what is L? Set of L labeled training examples. So you append 1 or 0, and then for Y you append 1. Okay. I wonder what this 32, 32, and 3 means. The dimension of X train, probably. Or does this mean the pixel value? Check. I think so. I think this is the... It has 9 labels. 32 by 32 color training images. Over 10 categories. Still don't understand what this shape is. 32 by 32 color, I get that. Color training images. Probably like pixels. But what is this 3? I don't know. Oh, maybe it's RGB. What is that? Why? 3 color gradients. Okay. Yeah. That makes perfect sense. All right, got that. Label that sets label data set size 4,000. But then why are we using only 1,000 here for labeled training examples? Shouldn't it be 4,000? Okay, anyways. This is 4,000 divided by 10, which is 400. So if positive counter is equal to 400, and negative counter is equal to 400, set 4,000 minus 400. What? Negative 3,600. No, it's just 3,600. Negative counter is equal to 3,600. 400 and 3,600. But where are these numbers coming from? It's like totally random. I don't understand. So 400 and 3,600, it breaks. Okay, whatever. So it totals up to 400 positive counters and 3,600 negative counters. That equals to 4,000. Okay. So if y train is equal to 1, okay, if it's at the limit, then you just continue. Otherwise, we increment the positive container, positive counter, and append it to our set, which only consists of 1,000. 1,000 images, 100 images of each class. Stratifying the labeled dataset. And U is the set of unlabeled examples. Okay, it's somehow training it here. But I want to continue with this tomorrow, as this stream is going on pretty late. What I'll do is go through this code right here. Actually, this one. Or I might write an article. Actually, yeah, writing an article might be a better idea. Okay.